A galaxy existed 290 million years after the beginning of everything, and it was already full of oxygen. Its light has been traveling toward us for 13.4 billion years. The gold mirror that caught it cost $10 billion to build and 25 years to launch. And what the mirror found inside that light should not have been there at all. In May 2024, astronomers confirmed the discovery using the Atacama Large Millimeter Array in Chile. Two independent teams, the same result, at a confidence level that left no room for doubt. The galaxy had 10 times more heavy elements than any model said was possible at that age. It had lived through multiple generations of stars being born and dying before any model said the first generation could have finished, and it was not alone. For years, cosmologists believed they understood how the universe assembled itself. They were right that the answers were coming. Then, in December 2021, a rocket rose from the jungle on the northeastern coast of South America. What the telescope aboard that rocket has found since, galaxy by galaxy, measurement by measurement, anomaly by anomaly, has forced the most successful model in the history of cosmology to confront the possibility that something, somewhere in its foundations, is wrong. We will trace how that model was built, examine what the telescope found that it cannot explain, and sit with what it means when the most powerful observatory ever launched looks at the early universe and sees something that was not supposed to be there. If this is the kind of story that keeps you up at night, subscribe, and consider hitting like so others can find it. Something is being discovered right now, not an answer. Something more unsettling than that. Let's begin. It was Christmas morning. Across the planet, children were tearing open wrapping paper. Families were gathering around tables. And on a launch pad carved out of the jungle on the northeastern coast of South America, a rocket sat in the dark, waiting to carry something that had taken the better part of 30 years to build. The people who understood what was riding on that rocket were not celebrating. In control rooms in Baltimore and across Europe, engineers sat with their hands folded and their eyes fixed on screens. Some of them had given decades to this machine. Some had already retired before it was ready. A few had not lived to see the morning at all. The rocket was an Ariane 5. The payload was the James Webb Space Telescope. The launch window opened at 7:32 in the morning local time, and when the countdown reached 0 and the engines ignited and the rocket climbed into the pale sky above the tree line, nobody cheered. They were too frightened to cheer. They had spent years cataloguing everything that could go wrong. The list had a number at the bottom, 344. 344 single points of failure. Individual steps during deployment where a single mechanical mistake, a single stubborn latch, a single motor drawing too much current or too little would end the mission permanently. No shuttle could fly up and fix it. There would be no second chance. The telescope was already moving away from any helping hand, and it was heading farther still. To understand why the tension in those control rooms was so extreme, you have to understand what the telescope actually was. Not just what it cost, $10 billion, though that number is almost too large to feel, but what it required of physics and engineering to exist at all. Start with the mirror. 6.5 meters across, roughly the width of a large living room. 18 individual hexagonal segments, each one shaped from beryllium, a metal chosen because it is both lightweight and extraordinarily stable at the temperatures the telescope would need to reach. Each segment was then coated in a microscopically thin layer of gold, chosen because gold reflects infrared light better than almost any other material. Assembled together, those 18 segments formed one of the most precise optical surfaces ever manufactured by human hands. But a mirror 6.5 meters wide cannot fit inside a rocket fairing. The engineers had known this from the beginning. The solution was a design that had never been attempted at this scale. Fold the mirror like a flower, launch it in pieces, and then rebuild it in space. The central core of 18 segments collapsed down, with 2 side panels hinging inward, like wings tucking against a bird's body. The whole structure had to compress into a shape narrow enough for the Ariane 5 and then unfold perfectly, millions of miles from the nearest tool or technician. The sunshield posed a different kind of problem entirely. To see in infrared, a telescope must be extraordinarily cold. Any warmth, including the warmth radiating from the telescope's own structure, would contaminate the signal. The instruments needed to operate at temperatures close to absolute zero, far colder than the frozen vacuum between most stars. To get there, the telescope needed to be shielded from every possible source of heat. The sun, the reflected light of Earth, even the warmth of the moon. The solution was a 5-layer thermal barrier, 69.5 feet long and 46.5 feet wide, made of a material called kapton. Each layer aluminized to reflect heat. The whole structure was roughly the size of a tennis court and as thin as a human hair. On the sun-facing side, the shield absorbs enormous heat. On the telescope side, the temperature drops to nearly nothing. That gradient, across just a few feet of layered film, spans hundreds of degrees. All of this had to be folded, like the mirror, into a shape compact enough to fly, and all of it had to unfold, flawlessly, in the vacuum of space. The deployment sequence began almost immediately after the rocket separated. 31 minutes after launch, the solar panels deployed, power flowing for the first time. The engineers allowed themselves a fraction of a breath. Then came the sunshield. 5 days of agonizing incremental extension, each of its hundreds of mechanical steps driven by pre-programmed commands at distances too great for any real-time correction. Motors reeling in cables, booms extending, membranes pulling flat. Any snag, any tangle would crumple the shield into useless wreckage. The layers separated, the shield tensioned. The cold side of the telescope began, very slowly, to cool. Then the secondary mirror swung out on 3 thin support struts. Then the 2 side panels of the primary mirror hinged outward. Each hinge had to rotate to an exact angle and lock permanently. There was no mechanism to correct them if they stopped short. In early January 2022, the panel deployments were confirmed. Controllers in Baltimore called out each latch as it engaged. A room that had been holding its collective breath for nearly 2 weeks allowed itself briefly to feel something other than dread. But the telescope was still not ready. The 18 mirror segments, now extended, were each slightly out of alignment. Engineers began a weeks-long campaign of minute adjustments, nudging each segment by fractions of a millionth of an inch, using small actuators on the back of every hexagon, watching the 18 ghost images of a distant star called HD 84406 slowly converge into one. On the 11th of March 2022, the final alignment check came back clean. 18 segments were one mirror, one perfect mirror, colder than almost anything in the natural universe, parked nearly 1 million miles from home, pointed at the oldest light in existence. The original plan had called for a launch in 2007. That date came and went. Then another and another. The mirrors were redesigned. The sunshield was redesigned. The budget doubled and then doubled again. Researchers who had devoted their careers to this machine watched deadline after deadline slide past. John Mather, a Nobel laureate who had been working toward this moment since the 1980s, stood in French Guiana on Christmas morning and watched the Ariane 5 rise into the sky. He did not celebrate. Nobody did. Not yet. The telescope was built to see the first light ever released in the universe. Light so ancient and so faint that it had spent the entire history of the cosmos traveling toward a mirror that did not yet exist when it began its journey. What cosmologists expected that light to reveal, they had worked out over decades of increasingly confident calculation. Before we see what the telescope actually found, we need to understand what the field believed, because the weight of what came next is only felt in full against the certainty of what came before. Before the James Webb Space Telescope ever turned its mirror toward the sky, cosmologists believed they understood, in broad and confident terms, how the universe worked. That confidence was not arrogance. It was earned, built piece by painstaking piece over decades of observation, calculation, and experimental confirmation. The model they had assembled was called lambda cold dark matter, and it was, by any measure, one of the most successful scientific frameworks ever constructed. Here is what it says. The universe is made of three components, none of which are evenly matched. Only 5% of everything that exists is ordinary matter. Atoms, molecules, the stuff that makes up stars and planets and oceans and you. 27% is something called cold dark matter, invisible to light, detectable only through its gravitational effects on the galaxies it surrounds, never directly observed in any laboratory despite decades of searching. The remaining 68% is stranger still, a property of space itself called dark energy, which drives the accelerating expansion of the universe. Together, these three ingredients in those precise proportions reproduce almost everything astronomers can observe. The model also described, with remarkable specificity, how structure formed. In the earliest moments after the Big Bang, the universe was a near-uniform fog of hydrogen and helium, with tiny fluctuations in density scattered throughout, regions that were fractionally denser than their surroundings, and regions that were fractionally emptier. Gravity pulled at those fluctuations. The denser regions attracted more matter. Over hundreds of millions of years, the fog collapsed into the first stars, and those stars gathered into the first small, faint, disorganized galaxies. And those dwarf galaxies slowly merged and accumulated into larger ones. Small first, large later. That process, called hierarchical structure formation, was one of the model's most fundamental and most tested predictions. It described the universe assembling itself the way a city grows from scattered settlements into a metropolis, gradually, across immense stretches of time. Heavy elements were a key part of that story too. The Big Bang produced essentially no oxygen, no carbon, no iron, no silicon. Those elements did not exist until the first generation of stars forged them in nuclear furnaces and then scattered them across space in violent supernova explosions. After those explosions, a second generation of stars could form, incorporating the debris of the first. Then those stars died, and a third generation formed, richer still. Each generation left the universe more chemically complex than it found it. Astronomers calculated that building up a meaningful quantity of oxygen, enough to detect spectroscopically in the light of a distant galaxy, required at least 1 billion years of this cycle: stellar birth, stellar death, and recycling. That was not a rough estimate. It was a carefully derived figure, anchored in the known physics of how stars burn and how they die, confirmed by observation and incorporated into the standard picture as one of its firmest chronological anchors. You could not have detectable oxygen earlier than that. The physics simply did not allow it. For decades, every observation pointed the same way. The Hubble Space Telescope peered into deep space and found exactly what lambda cold dark matter predicted. The farther back you looked, the smaller and less developed the galaxies appeared. The universe had assembled itself gradually, the way the model said it should. It was ordered. It was elegant. It was consistent. By the early years of the 21st century, cosmologists had accumulated so many confirming observations that many in the field began to wonder whether the great questions of cosmology might actually be answered within their lifetimes, not resolved in some distant future, not left to the next generation, answered soon by people working now. There is a particular kind of confidence that comes from a model that has been tested repeatedly and never broken. It is different from certainty. Most working scientists would never claim certainty. But it is close enough to certainty that it shapes how fields organize themselves, how resources are allocated, how graduate students are trained, and which questions are considered worth asking. Lambda cold dark matter had reached that point. It was not merely a theory in a textbook. It was the organizing principle behind billions of dollars of telescope time, behind every major cosmological survey of the previous 2 decades, behind the careers of hundreds of researchers worldwide who had structured their professional lives around its predictions. That weight matters. It matters because when something begins to go wrong with a model that carries that kind of institutional mass, the reverberations are not merely scientific. They run through dissertations and grant applications and university courses that have been taught for years without revision. They run through the assumptions embedded in every instrument design, every survey strategy, every question a researcher believed they already knew the shape of the answer to. The model had not just been confirmed, it had been inhabited. Lambda cold dark matter had earned its position. Slowly and rigorously, the field had won a coherent story about how the cosmos evolved from a featureless fog into the structured web of galaxies that surrounds us today. That story had been tested against observation after observation and had not failed. Its core predictions, small galaxies first, heavy elements built slowly across billions of years, the universe assembling itself from the bottom up, had stood firm across every instrument that pointed at the early universe. The James Webb Space Telescope was designed, among other things, to push that story further back in time, to see the first galaxies in the act of forming, to watch hierarchical structure beginning, to confirm, with unprecedented depth and resolution, that the universe had done what the model said it did. It launched on Christmas morning 2021. It spent 6 months aligning its mirror and calibrating its instruments. And then, in July 2022, it opened its eyes. On the 12th of July 2022, the President of the United States stood before a screen at the White House and unveiled the first official science image from the James Webb Space Telescope to the world. What the world saw stopped people in their tracks. A field of thousands of galaxies, each one a different color, each one a different shape, spirals and ellipses and smeared arcs of distorted light, covering a patch of sky so small that if you held a grain of sand at arm's length, it would cover that entire region. Every point of light in the image was not a star. Every point of light was a galaxy, containing hundreds of billions of stars, and the image reached farther back in time than any photograph in human history. There is something that happens when you look at that image and truly understand what you are seeing. It is not quite awe, though awe is part of it. It is closer to vertigo, a physical sense of the ground shifting as the mind tries to hold the actual scale of what the eyes are taking in. Each of those smears of color is not a nebula or a cluster. Each one is an entire universe of stars. And behind the nearest ones, distorted and stretched by the gravity of the galaxy cluster in the foreground, are galaxies that have been traveling toward that mirror for 9 billion, 10 billion, 13 billion years. You are not looking at a photograph. You are looking at a window into the past, stacked 13 billion years deep. The celebration was genuine and widespread. Scientists and journalists and members of the public stared at the image and felt something they struggled to name. Astronomers who had spent their careers fighting for this telescope, who had watched it miss deadline after deadline, who had waited through 30 years of delays and budget fights and near cancellations, allowed themselves for a moment to simply feel it. But in research offices at universities across the world, some astronomers were looking at those early images with a feeling that sat differently from celebration. Among them was Garth Illingworth, an astronomer at the University of California, Santa Cruz, who had been studying distant galaxies for decades and who understood, as well as anyone alive, what those galaxies were supposed to look like at various stages of cosmic history. The model was clear on this. Early galaxies should be small. They should be faint. They should look like the raw material from which larger structures would eventually be assembled, disorganized, primitive, still finding their shape across hundreds of millions of years. What Illingworth and others were seeing in the Webb data did not look entirely like that. Some of those objects looked unexpectedly large. Some looked unexpectedly bright. They carried a kind of structural maturity that, according to the model, they should not yet have had time to develop. And the effect was visible not in one or two outliers, but across the population of early objects in those first images. Richard Ellis, a cosmologist at University College London, and one of the most respected observational astronomers alive, was among the first to say something publicly. Looking at the early data, he told colleagues it worried him slightly that they were finding what he called monsters in the first few images. That word, monsters, was not hyperbole. He meant it precisely. These galaxies, if the measurements held up, were too massive to have formed in the time available to them. One word began circulating in private conversations among researchers. The word was wrong. That alone would have been remarkable. But there was a second layer to the unease that was harder to articulate and harder to dismiss. The sample size in those first images was tiny. Webb had been operational for only a few months. The area of sky covered was a fraction of the total observable universe. And yet already, in that minuscule slice, the data contained objects that strained the model's predictions. If the anomalies were real rather than instrumental artifacts, if they were features of the universe rather than quirks of the measurement, then the statistical implication was stark. There should be many more of them. Across the entire sky, at all the distances Webb had not yet examined, the universe might be filled with early massive galaxies that the standard framework had never anticipated and could not explain. The first images had been a celebration, but for the people who knew what to look for, they had also been a warning. The difficulty, at that stage, was that unease is not evidence. Private conversations are not science. Eyeballing an image and saying something looks wrong is the beginning of an investigation, not the conclusion of one. The anomalies needed to be measured. They needed to be quantified and submitted to the full apparatus of scrutiny that the field had built over decades for exactly this purpose. A galaxy that looks large might be a measurement artifact. A galaxy that looks bright might be contaminated by something in the foreground. The early images were suggestive. They were unsettling. They were not yet proof of anything. The skeptical response was not denial. It was method. The field had learned over generations to be cautious about first impressions, and every serious researcher understood that the instruments were new, the calibrations still being refined, and the techniques used to estimate early galaxy distances and masses carried real uncertainties. But unease has a way of persisting when it is grounded in something real. The researchers who were uneasy about those first images were not naive. They knew what the model predicted. They knew what the galaxies were supposed to look like, and what they were seeing, even allowing for every reasonable source of error, looked different. For that unease to become science, the field would need a paper. It would not have to wait long. On the 23rd of February, 2023, a paper landed in the journal Nature that moved the conversation from whispered concern to open confrontation. The authors were Ivo Labbé, an astronomer at Swinburne University of Technology in Australia, and Erica Nelson at the University of Colorado Boulder, along with a team of colleagues that included Peter Van Dockum of Yale and Joel Leger of Penn State. They had been analyzing early Webb photometric data, measuring the light arriving from extremely distant objects. And what they had found was difficult to process, even for the people who found it. 6 candidate galaxies, all of them existing between 500 and 700 million years after the Big Bang. And their masses, if the measurements held up, were extraordinary. Up to 100 billion solar masses, 100 billion times the mass of our own star. Some of these objects, if confirmed, would rival the Milky Way in size. The Milky Way took approximately 13 billion years to build. These candidates had apparently assembled something comparable in less than 700 million years. Lambda cold dark matter had a specific and explicit prediction for this era. Early galaxies should be small. They should look like infant clumps of gas and newborn stars. The seeds, the raw material, the building blocks from which larger galaxies would eventually be assembled across billions of years of mergers and accretion. The model did not allow for fully grown adults sitting in the cosmic nursery. There was not enough time. The physics of how gas cools and collapses and ignites into stars simply could not produce objects of this size and mass in the available window. What the data seemed to show instead was exactly that: adults in the nursery. Labbé himself described the situation plainly. They had never observed galaxies of such colossal size this early in cosmic history. They were too big, he said, to even exist within current models. Joel Leger, who worked with Leger's team analyzing the candidates, offered a verdict that spread quickly through the astronomical community. These objects, he said, were in tension with 99% of cosmological models. He chose his words carefully. He did not say the models were wrong. He said that 99% of them could not account for what the data appeared to show. That is a different claim, and in some ways a more devastating one, because it leaves open the door to the possibility that the right model exists somewhere in the remaining 1%, while simultaneously acknowledging that the entire mainstream framework is failing. Erica Nelson put it more directly, It was just crazy, she said, that these things seem to exist. Think about what the violation actually represents. A galaxy of 100 billion solar masses at 500 to 700 million years after the Big Bang is not merely an outlier at the edge of what the models could accommodate. It is a contradiction of the timeline of cosmic history, in the same way that a fully grown oak tree contradicts any explanation that it grew from an acorn planted last week. The tree is the right species. The chemistry is correct. The rings are genuine. But the time is impossible, and the impossibility is not a matter of degree. It is categorical. Understand what was at stake in that confrontation. Lambda cold dark matter was far more than a theory in a textbook. It was the organizing framework behind every major deep sky survey of the previous 2 decades, behind the careers of hundreds of researchers, behind the questions written into the funding proposals that had paid for the instruments now producing this data. If it was seriously wrong, not wrong at the margins, but wrong in its central prediction about how the first galaxies formed, then entire research programs would need to be reconsidered. Textbooks would need rewriting. The coherent story of cosmic history that science had spent 50 years assembling would develop cracks that nobody knew how to fill. These were not abstract stakes. They were personal, professional, and in some cases, the work of entire lifetimes. The community fractured along predictable lines. Established researchers who had built careers on lambda cold dark matter pointed immediately to the error bars. Photometric measurements, they noted, are estimates derived from the color and brightness of light across several wavelength bands, not direct measurements of distance or mass. They could be wrong. They were often wrong. Redshift estimates made this way, called photometric redshifts, had fooled astronomers before. Dust inside a galaxy absorbs blue light and re-emits it as red, making a galaxy look more distant than it actually is. Active galactic nuclei, the energetic cores of galaxies hosting massive black holes, can also inflate apparent brightness, making an object appear far more massive than its stellar content alone would justify. These were not frivolous objections. They were the correct objections to raise, and raising them was exactly what the scientific process required. But the data was the data. There were 6 of them, all identified in a small early sample before Webb had even begun its deep systematic surveys. The implication, if they were real rather than instrumental artifacts, was not that cosmologists had made a minor error. The implication was that something fundamental about the early universe had been misunderstood, something about how fast matter could organize itself into galaxies, something about the conditions that existed in those first few 100 million years. And crucially, the anomalies had been found in a fragment of sky so small as to be almost nothing. If objects like these existed in that fragment, they almost certainly existed throughout the early universe at large. The full sky had not been surveyed. The telescope had been operating for months, not years. Whatever lay in the unseen depths, the first samples alone were already enough to force the question. The field had been confronted for the first time with a genuine and quantified challenge to one of the model's most central predictions. And the instrument doing the challenging was only warming up. The photometric candidates needed to survive a far more rigorous test before anyone could say with confidence what they were looking at. That test was already being prepared, in observatories around the world and in the queue of the telescope itself. It was called spectroscopy, and it would not be gentle. Science does not collapse under pressure, it argues back. And in the months following the Labbe and Nelson paper, the arguments came hard and fast, which is precisely how the process is supposed to work. The first line of attack was methodological. Photometric redshifts, critics pointed out, carry significant uncertainty. When you measure a galaxy's distance by analyzing how its light is distributed across different wavelength bands, you are making an inference based on assumptions about what that galaxy's light should look like. Those assumptions can be wrong, and they can be wrong in systematic ways. Dust inside a galaxy absorbs blue light and re-emits it as red, making the galaxy appear more distant than it actually is. Active galactic nuclei, the energetic cores of galaxies, where supermassive black holes are actively consuming surrounding gas, can flood a galaxy with so much light that its apparent stellar mass is dramatically inflated. A galaxy that looks enormously massive from a photometric measurement might, under spectroscopic examination, turn out to be a far more modest object lit up by a central black hole, rather than by the collective glow of 100 billion stars. These were not frivolous objections. They were the correct objections, raised by careful researchers who had seen exactly this kind of error before. The history of observational astronomy is full of objects that looked extraordinary until someone took a spectrum. The appropriate response to the Labbé and Nelson candidates was not celebration or alarm, it was scrutiny. To understand what spectroscopy offers that photometry cannot, it helps to think about what each technique actually does. Photometry measures the total brightness of an object across a handful of broad color bands. Essentially, how bright something is in blue light, in green light, in red light, in near-infrared. From that pattern of brightnesses, you can make inferences about the object's distance and properties. It is a powerful technique, but it is an inference chain, and every link in that chain introduces uncertainty. Spectroscopy is different in kind, not just in degree. Instead of measuring brightness across a few broad bands, it splits the incoming light into thousands of individual wavelengths and reads what is there. Every element in the universe produces light at specific wavelengths, a chemical fingerprint as distinctive as a barcode. Hydrogen emits at known wavelengths. Oxygen emits at known wavelengths. Carbon, magnesium, iron, each has its own signature. When you observe those signatures in the spectrum of a distant galaxy and find them shifted toward the red end by a calculable amount, you can determine with great precision how fast the galaxy is receding and therefore how far away it is. Spectroscopy does not estimate distance. Given sufficient signal, it measures it. Through the latter half of 2023, the campaign began. Research teams around the world, and time allocated on Webb itself, set about obtaining spectra of the most dramatic photometric candidates. The process was slow and the data painstaking to analyze. Some candidates did not survive. A handful of the most extreme early claims were revised significantly downward when spectra arrived. The redshifts were not as extreme as the photometric estimates had suggested, and the masses were correspondingly more modest. The skeptics felt vindicated. The standard model breathed again. Then came the confirmations. The galaxies that survived spectroscopic scrutiny were fewer in number than the original photometric sample, but they were real. Not revised downward to comfortable territory, real and still anomalous. Verified not by one instrument or one team, but by multiple independent observations, each arriving at the same conclusion. The distances were confirmed. The masses, where directly measurable, held up. No active galactic nucleus contamination sufficient to explain the discrepancy. No dust reddening that could account for the apparent redshift. These objects existed where and when the photometric measurements had suggested, and they were as massive as the most conservative estimates indicated. What the skeptical campaign had accomplished paradoxically was to sharpen the problem rather than dissolve it. By eliminating the candidates that could be explained away, the objects where dust or central black holes or photometric error might account for the appearance, it left behind a residue that resisted explanation. A smaller number, but a cleaner one. Objects that sat in regions of the parameter space, where the standard model simply had no room for them. The individual rebuttals had been credible. The residue was not. Researchers who had spent months arguing that the initial results were measurement artifacts found themselves confronting a revised version of the same question. Not whether there was a problem, but how large the problem was. That is a very different conversation from the one that had been happening in February of 2023, and everyone who had followed the debate closely understood the difference. The field had entered a new phase. The anomalies had survived the most rigorous test the community could bring to bear. Something real was there. The question of what it meant remained entirely open, but the question of whether it existed had been answered. And the Webb survey was still running. The JADES program, the James Webb Advanced Deep Extragalactic Survey, had been systematically cataloguing galaxy populations across multiple deep fields for months, accumulating spectra and images of thousands of objects. Deep within that catalogue, waiting in a data set that several team members had already checked and rechecked expecting to find an error, was something that would make the Labbe and Nelson candidates look, in retrospect, like the opening act. The JADES survey was not designed to break records. That distinction matters because it shaped how the team interpreted what they found. The James Webb Advanced Deep Extragalactic Survey was built on a different philosophy from the searches that had produced the early alarming photometric candidates. Its goal was not to hunt for spectacular outliers, but to map the galaxy population in the early universe systematically, layer by careful layer, the way a geologist reads rock strata. Point the telescope at two carefully chosen patches of sky, regions already studied extensively by Hubble and ground-based observatories, and stare. Hundreds of hours of exposure time, every instrument active, every photon counted, build a complete, statistically meaningful catalogue rather than a collection of dramatic individual objects. Kevin Heinlein at the University of Arizona and Stefano Carniani at the Scuola Normale Superiore in Pisa were among the researchers leading parts of the analysis. They were not looking for something impossible. They were trying to understand the ordinary architecture of the early universe, what a typical galaxy looked like at various moments after the Big Bang, how the population evolved, how quickly structures assembled across cosmic time. What they found in the deepest part of the catalogue was not typical of anything. In October 2023, and again in January 2024, the NIR SPEC instrument on the James Webb Space Telescope spent nearly 10 hours observing a single object. When the spectrum came back and was first processed by the team, the evidence was unambiguous. The galaxy, catalogued as JADES-GS-Z14-0, had a spectroscopic redshift of 14.32. That number required translation to be felt properly. A redshift of 14.32 means that the light captured by the telescope left this galaxy just 290 million years after the Big Bang. The universe, by the best current measurements, is 13.8 billion years old. 290 million years is roughly 2% of that total age. The universe was, cosmically speaking, a newborn, and this galaxy was already there. That alone was remarkable, but it was not the deepest shock. The deeper shock was what the galaxy contained and what it looked like. In terms of physical size, JADES GS-Z14-0 spans approximately 1,600 light-years across. Compare that to our own Milky Way, which stretches roughly 100,000 light-years from edge to edge. The JADES galaxy sounds small, and by any modern standard it is. But the age is the issue. At 290 million years, it should not be 1,600 light-years. It should be a smudge. It should be a protogalactic fragment barely distinguishable from the surrounding intergalactic gas. Its stellar mass, approximately 500 million solar masses, was already enough to challenge models of how quickly gas can cool, collapse, and ignite into stars at such an early time. Every atom in it had to have been forged and assembled in a cosmos that had existed for less than 2% of its current lifespan. Then the mid-infrared instrument detected something in the galaxy's light that the team kept returning to, expecting to find an error. There was no error. The spectral signatures indicated the presence of strong ionized gas emission, and within that emission, lines consistent with oxygen. The team was cautious. A single instrument's hint of oxygen in a galaxy at this distance, at this age, was extraordinary enough to demand confirmation from something more powerful and more precise. What followed, in late 2024, was one of the most striking sequences in the history of observational astronomy. Two independent teams of researchers, one led by Sander Schoes at Leiden Observatory in the Netherlands, one led by Stefano Carniani at the Scuola Normale Superiore in Pisa, simultaneously analyzed observations of JADES-GS-Z 14-0 obtained with the Atacama Large Millimeter Array, a network of radio dishes in the Chilean desert that can detect the faint sub-millimeter radiation emitted by cold gas in distant galaxies. Both teams, working entirely independently and using different analytical approaches, found the same thing: an oxygen emission line detected at a confidence level of 6.6 sigma, a threshold so high that the probability of it arising from random noise is less than 1 in a billion. The signal was real. The ALMA detection also allowed the teams to refine the galaxy's redshift with extraordinary precision. Where the original NIR spec measurement had placed it at a redshift of 14.32, the oxygen line's exact position in the spectrum pinned the redshift down to 14.1793, with an uncertainty of just 7/10,000ths. That improvement in precision was a factor of more than 180 over the original measurement. But precision was not the revelation. The revelation was what having oxygen at all meant. Oxygen does not form in the Big Bang. The Big Bang produced hydrogen, helium, and trace amounts of lithium, and nothing heavier. Every other element in the periodic table was forged later, inside stars. Oxygen specifically is produced in the cores of massive stars, stars many times heavier than our Sun, through a sequence of nuclear fusion reactions, and it is released into the surrounding galaxy only when those stars end their lives in supernova explosions. For oxygen to be present in detectable quantities inside a galaxy, that galaxy must have already hosted at least one, and likely multiple generations of stars that were born, burnt through their nuclear fuel, and died violently. That process takes time. The Standard Model placed the minimum timescale for building a chemically mature galaxy at least 1 billion years. JADES GS Z14-0 was doing it at 290 million years, and according to both ALMA teams, the galaxy had approximately 10 times more heavy elements than any model had predicted would be possible at that epoch. Carniani, who led the Italian team, expressed the difficulty with characteristic plainness. How, he asked, can nature make such a bright, massive, and large galaxy in less than 300 million years? It was not a rhetorical question. He and his colleagues genuinely had no answer. Schoes, the lead author of the Dutch team, reached for an analogy. It is like finding an adolescent, he said, where you would only expect babies. The light from this galaxy traveled 13.4 billion years to reach the Webb mirror. Due to the expansion of the universe during that journey, the galaxy now sits at a proper distance of approximately 33 billion light-years from Earth. We are not looking at something that exists in the universe as it is today. We are looking at a message sent before our planet, before our star, before most of the stars in the Milky Way were born. And that message says, we were already here. We had already lived and died and scattered our remains across space. Whatever came before us, you have not yet found it. The question that hung at the end of every conversation about JADES-GS-Z 14-0 was the same. If oxygen was present at 290 million years, then stars must have formed and completed their lives before any current instrument could observe what existed in that earlier window. The telescope was seeing the aftermath of a history it could not yet read. For a few months, this was the most distant confirmed object in the observable universe. Then the record fell again. The survey had a name that acknowledged what it was looking for, and what it feared it might not find. The Mirage, or Miracle Survey. The question embedded in that name was specific and honest. Were the extremely distant galaxy candidates that Webb had been finding since its first science release genuinely what they appeared to be? Objects from the earliest moments of cosmic history, luminous and massive far beyond what any model predicted? Or were they mirages? bright, unusual objects, whose apparent distances were optical illusions, artifacts of the measurement rather than features of the universe. The team running the survey was led by Rohan Naidu of the Kavli Institute for Astrophysics and Space Research at the Massachusetts Institute of Technology. Peter Van Dokkum of Yale University was among his collaborators. They had aimed 5 pointing positions of the Webb telescope at fields containing the most promising high redshift candidates, and they had obtained spectroscopic follow-up to find out which were real. One of those candidates stood out from the moment it appeared in the imaging data. It disappeared entirely in the shorter wavelength filters, vanishing in the infrared bands where a nearer galaxy would still show some faint trace, and blazed into brightness only at longer wavelengths. That disappearing act was the signature of an object at extreme distance, its shorter wavelength light absorbed by the intervening hydrogen along the line of sight. The team designated it MOM-Z14, the letters standing for the survey's name. In January 2026, the paper announcing its confirmed properties was published in the Open Journal of Astrophysics. The spectroscopic redshift, confirmed through Webb's NIR-SPEC instrument via a sharp spectral break and detections of 5 emission lines in the rest frame ultraviolet, was 14.44. Its light had been traveling for approximately 13.5 billion years. The galaxy exists 280 million years after the Big Bang, 10 million years earlier than JADES-GS-Z14-0, making it the most distant confirmed object in the observable universe. Van Dokkum described what that meant in terms designed to make the number land. At the moment of the paper's publication, he said, MOM-Z14 was the most distant object known to humanity. And to put the age in context, he offered a comparison. Sharks have been swimming in Earth's oceans for approximately 450 million years. They existed before the first trees. They survived the extinction that killed the dinosaurs. They are, by any measure of biological history, extraordinarily ancient. This galaxy is younger than sharks. The galaxy itself, under spectroscopic examination, proved to be deeply unusual in ways that went beyond mere distance. Its effective radius, the distance from its center within which half its total light is emitted, is approximately 74 parsecs, which translates to roughly 241 light-years. For reference, the Milky Way spans about 100,000 light-years from edge to edge. MOM-Z14 is extraordinarily compact, about 50 times smaller than our own galaxy. But its compactness was not what attracted the most attention. What attracted attention was its chemistry. The spectra showed no signs of an active galactic nucleus. Whatever was producing the galaxy's luminosity was not a feeding central black hole amplifying its apparent brightness. The light was coming from stars, and the stars were forming at a startling rate. The galaxy's star formation history showed that it had increased its rate of star production by a factor of approximately 10 in the 5 million years preceding the observations, compared to the 50 million years before that. The universe was producing new stars inside this object, at a pace that compressed timescales the standard model did not accommodate. More striking still were the spectral signatures of nitrogen. The relative abundance of nitrogen compared to carbon in MOM-Z14 was unusually high, a chemical pattern that, in the present-day universe, is associated almost exclusively with a specific type of environment: globular clusters. These are the ancient, dense balls of stars that orbit the halo of the Milky Way and other galaxies, dating back nearly to the beginning of cosmic time, forged in conditions that no longer exist in the modern universe. Finding that same chemical signature in a galaxy, just 280 million years old, was pointing towards something extraordinary. Supermassive first-generation stars, formed in the dense conditions of the earliest cosmic environments, stars whose nuclear reactions could produce the unusual nitrogen excess the spectra were showing. There was also something strange in the galaxy's immediate surroundings. The spectral data showed tentative evidence of a partially ionized bubble of hydrogen around MOM-Z14, a region where the surrounding fog of neutral hydrogen had already been cleared away by the galaxy's ultraviolet radiation. This was unexpected for a galaxy at this redshift. Every model of cosmic reionization predicted that at 280 million years, the universe should have been essentially opaque, the surrounding hydrogen 100% neutral, not yet disturbed by the first light sources. MOEM Z14 was showing signs of having already punched a hole in that fog. Naidu, reflecting on what his team had found, was direct about how far outside the boundaries of expectation they had traveled. Webb, he said, had revealed a stunning population of bright galaxies at surprisingly early epochs, where few such sources were expected. It looked nothing like what anyone had predicted, but the most important number in the paper was not a property of MOM-Z14 itself. It was a statistical inference that MOM-Z14 and JADES-GS-Z14-0, taken together, forced onto the field. The two galaxies were found in a combined survey area of approximately 350 square arc-minutes, a genuinely tiny fraction of the total observable sky. From this small sample, the teams were able to estimate how abundant objects like these should be across the full sky. The answer, when expressed as a ratio against what the pre-Webb consensus models had predicted, was 182 times. Not 182% more abundant than expected, not twice as common or 10 times as common, 182 times more common. The number of bright, luminous early galaxies in this redshift range, implied by the survey, exceeded every pre-launch prediction by nearly 2 orders of magnitude. That number does not describe a refinement. It does not describe a minor adjustment to a well-functioning model. It describes a systematic failure of prediction at one of the most fundamental levels cosmology operates on. The question of how many galaxies of a given luminosity should exist at a given moment in cosmic history. Whatever the early universe was doing with its matter and energy in the first 300 million years, it was not doing what the model said. Both of these anomalies, the oxygen in a galaxy too young for it, and the abundance of luminous early galaxies 182 times beyond prediction, concerned what the early universe had managed to build. A third anomaly was different in character. It concerned how the early universe was lit, and it required understanding a phenomenon that had been erased from the sky for 13 billion years. After the Big Bang cooled enough for the first neutral atoms to form, the universe went dark. Not gradually, not partially, dark. There were no stars yet. There were no galaxies. There was only hydrogen and helium, the first simple atoms, drifting in the near-uniform gravitational wells left by the earliest density fluctuations, cooling slowly as the universe expanded around them. For hundreds of millions of years, nothing in the cosmos produced light that could travel any significant distance. This period has a name. Cosmologists call it the Cosmic Dark Ages. Then the first stars ignited. As those earliest stars burned, and they burned hot, far hotter than most stars that exist today, they began releasing ultraviolet radiation in enormous quantities. That radiation began doing something to the surrounding hydrogen. It was ionizing it, stripping the electrons away from the hydrogen nuclei, turning neutral gas back into the plasma it had been in the first moments after the Big Bang. As more stars formed, and then the first galaxies, the process accelerated. Bubbles of ionized, transparent gas began growing outward from the earliest luminous sources. Over time, those bubbles expanded and merged. The fog burned away, region by region, until the universe became transparent to visible light. That transition, from opaque to clear, from a cosmos that absorbed everything to one that let light travel freely across billions of light years, is called reionization. The established timeline for when this happened was one of the firmest anchors in the Standard Model. Derived from observations of distant quasars, confirmed by the Planck satellite's maps of the earliest light in the universe, and cross-checked against multiple independent datasets over decades, the consensus held that reionization began around 400 to 500 million years after the Big Bang, and was essentially complete by 1 billion years. This was not considered tentative. It was one of the things cosmology knew. Central to understanding why what came next was so disruptive is a specific type of radiation called Lyman alpha. When a hydrogen atom absorbs an ultraviolet photon, its electron is excited to a higher energy level. When the electron drops back down, it releases a photon at a very particular wavelength, a wavelength so specific that it functions as a fingerprint. That emission, Lyman alpha radiation, is produced wherever young, hot stars are flooding their surroundings with ultraviolet light. It is a reliable signature of vigorous star formation. But neutral hydrogen, the kind that filled the universe before ionization completed, absorbs Lyman alpha with extraordinary efficiency. A photon emitted at this wavelength by a galaxy in the early universe would travel only a short distance before being captured by a hydrogen atom in the surrounding fog. It would simply vanish. The Standard Model was unambiguous on this point. Any Lyman alpha signal originating before ionization was effectively erased during transit. You would not detect it. The fog would swallow it before it could reach any telescope, no matter how powerful. In January 2024, Joris Wittstock of the University of Cambridge and the Cosmic Dawn Centre, along with a large international team of collaborators, was analysing spectroscopic data from a galaxy that had been identified in the JD's survey. The galaxy was at a redshift of 13.0, placing it just 330 million years after the Big Bang. In the resulting spectrum, something appeared that should not have been there. A Lyman alpha emission line, bright, singular, unambiguous, with an equivalent width above 40 angstroms. That level of Lyman alpha emission had previously only been observed at redshifts below 9, in regions of the sky where ionization had already advanced significantly and the surrounding hydrogen was predominantly ionized. At a redshift of 13, the universe should have been opaque to this signal. The fog should have caught it. The Standard Model said clearly and without qualification that this detection was impossible. Kevin Hainline of the University of Arizona, one of the team members who had contributed to the analysis, expressed the situation with the precise understatement that the moment deserved. "We really should not have found a galaxy like this," he said, "given our understanding of how the universe was at that time." The paper was published in Nature in 2025. The signal was real. The implications were severe. There are only a small number of ways that Lyman alpha radiation could have escaped from a galaxy at this redshift and reached the telescope. The first is that the galaxy had already created a large ionized bubble around itself, a cleared region of the surrounding hydrogen, large enough for the photons to escape before encountering the neutral fog further out. But for a bubble of sufficient size to have existed 330 million years after the Big Bang, ionizing radiation must have been burning through the surrounding hydrogen far earlier than any model predicted. The fog would have had to start clearing substantially sooner than the established timeline allowed. The second possibility is that the fog itself was never as thick as the models assumed, that the neutral hydrogen density in the very early universe was lower, patchier, more permeable in certain regions than the standard ionization timeline allows. Either interpretation leads to the same conclusion. Ionization began significantly earlier than cosmologists had calculated. Then, in March of 2026, new and deeper observations of the same galaxy, obtained as part of a program called OASIS, using 56 hours of accumulated Webb NER-spec time, confirmed the Lyman alpha detection with still higher confidence and resolved additional properties of the signal. The equivalent width was measured at 66 angstroms, even larger than the initial detection. The line was reaffirmed. The blue continuum slope of the galaxy's spectrum pointed toward an exceptionally hot and productive ionizing source. The signal was not going away. This was a direct detection. There was no inference chain between the telescope and the conclusion. The photons arrived. The wavelength was measured. The signal was Lyman alpha, from a time when Lyman alpha should not have been able to reach us. One of the firmest anchors in the chronology of the cosmos had slipped. Each of these findings, the galaxy with oxygen where there should have been none, The abundance of luminous early structures 182 times beyond prediction, the signal through the fog, shared something in common. They were things that the telescope had found, which, according to everything the field thought it knew, should not have been there. But the telescope had also looked directly at something, measured it carefully with every tool available, and still arrived at a wrong answer. Not because the telescope failed, because of something more fundamental than that. There is a useful distinction between finding something that should not exist and misidentifying something that does. The anomalies we have covered so far belong to the first category. What follows belongs to the second. And the second, in some ways, is the more unsettling of the two. In 2022, astronomers using the Hubble Space Telescope announced a discovery that had been considered essentially impossible. A single star, individually resolved, at a distance of approximately 12.9 billion light-years. To observe an individual star at that remove requires extraordinary circumstances. Stars at such distances are far too faint to be seen as individual objects. Their light blurs into the collective glow of their host galaxy long before it reaches any telescope. The only way to see one is if something between the star and the observer acts as a natural magnifying glass. That something is gravitational lensing. A massive object, in this case, an entire galaxy cluster positioned almost perfectly between the star and Earth, bends the light from behind it. When the geometry is precise, light from a single source can be focused along a line called a caustic, and the amplification factor along that caustic can be enormous, thousands of times, enough to take a star that would otherwise be invisible and boost it to something a telescope can detect. The star had been discovered riding exactly such a caustic. The team named it Earendel, after a figure in the mythology of J.R.R. Tolkien, whose name meant morning star in the Old English Tolkien drew on for his invented languages. The name was fitting. It was, at the time of its announcement, the most distant individual star ever resolved. The researchers published in Nature. The finding passed through peer review and withstood scrutiny. Press coverage was extensive and accurate. The record stood. Then the James Webb Space Telescope looked at Earendel. What Webb found did not match what Hubble had implied. The brightness profile of the source, examined at Webb's far superior resolution and infrared sensitivity, did not match the signature of a single star. Neither did the spectral data. What the observations matched instead was the signature of a star cluster, a dense grouping of potentially hundreds or thousands of individual stars packed closely enough together that, at this distance and at Hubble's resolution, they blurred into what appeared to be a single point of light. The record for the most distant individual star ever observed may belong to an object that is not, in fact, a single star at all. Pause on that for a moment. The researchers who studied Earendel using Hubble were not careless. Hubble was functioning exactly as designed. The analysis was rigorous and thorough. Every available tool was applied to the problem. The finding went through the full apparatus of scientific scrutiny, peer review, independent examination, public publication, and came out the other side as established knowledge. And the conclusion was wrong. Not wrong at the margins. Wrong in its most basic characterization of the object. One star versus hundreds or thousands of stars is not a quantitative error, it is a categorical one. This matters not because Earendel is uniquely important, but because of what it reveals about the relationship between observation and knowledge. Science depends on instruments, and instruments have limits. Every observation is filtered through the resolution, the sensitivity, and the wavelength coverage of the telescope that made it. What those instruments return is not the thing itself. It is a representation of the thing, shaped by every constraint the instrument operates under. Hubble's representation of Earendel was internally consistent, based on everything Hubble could see. It was also, when a better instrument looked at the same object, revealed to be a misrepresentation of what was actually there. There is an analogy that captures this imperfectly but usefully. Imagine navigating at sea by starlight, as sailors did for thousands of years. You learn the positions of the stars. You chart courses by them. You sail confidently, arrival after arrival, confirming that the method works. Then someone hands you an instrument that measures the actual positions of those stars without the distorting effects of atmospheric refraction, the bending of light as it passes through the layers of air above you, and you discover that the star you relied on most was not quite where you thought it was. Your charts were accurate relative to one another. Your navigation was internally consistent, but the fixed reference point on which the entire system depended was not where you believed it to be. Earendel is that shifted star, a fixed reference celebrated and built upon, which a better instrument revealed to be something other than what it appeared. This is not a failure of science. It is science working exactly as it must. Each generation of instruments exposing the limits of the previous generation's certainties and replacing approximations with something closer to the thing itself. The lesson is not that observation cannot be trusted. The lesson is that every observation carries an expiration date, measured in the lifespan of the next instrument capable of looking more carefully. And Webb, as it turned out, was looking more carefully at everything. The uncomfortable truth that Earendel illustrated was already visible across the full body of findings that the telescope had produced. What cosmology had built over decades was an extraordinarily precise and internally consistent picture of the universe. But precision and internal consistency are not the same as accuracy. A model that reproduces its own assumptions with great fidelity is still only as good as the observations that seeded those assumptions. Webb was showing, case by case, that some of those observations, some of the measurements on which the model rested, were approximations that the model had mistaken for solid ground. That lesson would reappear in sharper form when the telescope turned to one of the most fundamental measurements in all of cosmology. A single number on which the age, the size, and the future of the universe all depend. Every so often, science produces a number that becomes load-bearing, a value that so much else depends on that, if it shifts, the entire structure above it has to be reassessed. The Hubble constant is that kind of number. Named after Edwin Hubble, who first measured the expansion of the universe in the 1920s, the Hubble constant describes how fast the cosmos is currently growing. The unit it is expressed in, kilometers per second per megaparsec, translates roughly as follows. For every megaparsec of distance between 2 points in space, those points are moving apart at a rate of however many kilometers per second the constant specifies. A megaparsec is approximately 3.26 million light-years, which gives you a sense of the scales involved. Get the constant right, and you can calculate the age of the universe, the rate at which structure has formed, the future trajectory of cosmic expansion. Get it wrong, and every model built on top of it carries a hidden error through every calculation it makes. For decades, cosmologists argued about the Hubble constant's value without being able to measure it precisely enough to settle the dispute. By the early years of the 21st century, two methods had emerged as the most credible, and they disagreed. The first method looked backward in time. The Planck satellite had mapped the cosmic microwave background, the faint afterglow of the Big Bang, permeating every direction of the sky with nearly uniform radiation, with extraordinary precision. From those measurements, physicists could calculate how fast the universe was expanding in its earliest epochs and extrapolate forward to the present day using the standard model. The number that came back was 67.36 kilometers per second per megaparsec. The second method looked at the nearby universe directly. A team of researchers known informally as SH0ES, an acronym from the full name of their program, Supernovae H0, for the equation of state of dark energy, led by Adam Rees of Johns Hopkins University, a Nobel laureate, used Cepheid variable stars as distance markers. Cepheid variables pulse in a regular rhythm, and the period of that pulsation is directly related to the star's intrinsic brightness. Measure how bright it appears, compare it to how bright it should be, and you can calculate how far away it is with considerable precision. That distance then anchors measurements of type 1a supernovae. a specific category of stellar explosion that always reaches roughly the same peak brightness, extending the distance scale further out into the universe. The local expansion rate that this method produced was 73.04 kilometers per second per megaparsec. The gap between those two numbers is approximately 5 to 6 kilometers per second per megaparsec. That sounds small. It is not small. The statistical significance of the discrepancy had, by the early 2020s, reached 5 sigma. In particle physics, 5 sigma is the formal threshold for declaring a discovery. Reversed, a 5 sigma disagreement between two independent measurements of the same quantity is the formal threshold for saying something is seriously, possibly fundamentally wrong. This was not a matter of competing measurement techniques gradually converging on the same answer. This was two precisely obtained numbers pointing in different directions, and the gap between them was too large to dismiss. The natural explanation to reach for first was measurement error. The Hubble Space Telescope's resolution had limits, and in crowded stellar fields, where many stars are packed close together in the images, it was possible that faint companion stars were bleeding light into the Cepheid measurements, inflating their apparent brightness and therefore distorting the inferred distances. If the local measurement was being systematically biased upward by this kind of contamination, the tension might dissolve under more careful analysis. This was precisely the question that Webb was directed to investigate. Its resolution in the infrared is far sharper than Hubble's, and in those same crowded fields, it could separate individual stars that Hubble had blurred together. If the Cepheid measurements were being inflated by contamination, Webb would see it. In December 2024, Rees and the SH0ES team published their analysis using the largest Webb dataset assembled to that point. They had measured Cepheid variables across multiple galaxies using 3 independent methods: the Cepheid pulsation periods, carbon-rich asymptotic giant branch stars, and the brightness of the tip of the red giant branch, and cross-checked all 3 against the same galaxies where they had previously used Hubble. The combined result was 72.6 kilometers per second per megaparsec, essentially identical to the Hubble Space Telescope's value of 72.8 for the same sample. Crowding was not the problem. The local measurement was accurate. Rees stated the implication plainly. With measurement errors negated, he said, what remains is the real and exciting possibility that we have misunderstood the universe. A separate team, led by Wendy Friedman at the University of Chicago, analyzed a different set of Webb observations using different distance indicators, red giant branch stars and carbon-rich stars, and arrived at values between 68.4 and 71.5 kilometers per second per megaparsec, closer to the Planck figure. The field has not reached full consensus. Friedman's team argued that Cepheid-based measurements may carry systematic uncertainties that the other methods avoid. But the Rees measurement, using the most comprehensive dataset and multiple cross-checks, remains the most thorough local determination to date. The tension persists. Daniel Skolnick of Duke University, one of the cosmologists closely involved in these measurements, offered the assessment that had spread quickly through the field. The Hubble tension, he said, is now a Hubble crisis. 2 independent, carefully verified methods measuring the same quantity and arriving at different answers. 2 accurate anchors, one at each end of cosmic time, and a gap between them that the standard model cannot bridge. Mark Kamiankowski of Johns Hopkins, one of the theorists working hardest on the problem, described where that left the field. One possible explanation, he said, would be if something were missing from our understanding of the early universe, a new component of matter, early dark energy, that gave the cosmos an unexpected kick in its first moments and then vanished. Theorists, he added, have license to get pretty creative. That license has been exercised extensively. Each proposed solution to the tension introduces new physics that has not been directly observed. None of them are comfortable, and none of them, as of early 2026, has been confirmed. The expansion rate disagreement was a problem with a number. What came next was a problem with a shape. When Webb's first deep field images came back in the summer of 2022, astronomers noticed something that did not belong in any existing category. Scattered through the images, appearing among the galaxies and the gravitational arcs and the familiar shapes of cosmic structure, were small, extraordinarily compact, intensely red points of light. They were present in numbers that surprised the researchers studying the data. They were clustered in the first billion years of cosmic history, appearing when the universe was young, and then, roughly a billion years later, seeming to disappear. Which was itself strange, because objects do not simply vanish from the universe, and whatever process was causing them to fade from view at later times was not immediately obvious. Astronomers called them little red dots, because that is what they were: tiny, red, and impossible to explain. By 2024, 341 of them had been catalogued. By early 2026, the number was approaching 1,000. In the 3.5 years since their discovery, the field had produced 4 distinct explanations for what they were. Each one, upon closer examination, had failed. The first explanation, proposed in 2022, was that little red dots were compact starburst galaxies, regions of furious star formation so dense and energetic that the ultraviolet light pouring from the young hot stars inside them had been redshifted into the infrared by the expansion of the universe. It was a reasonable first guess. It was consistent with the general principle that the early universe contained unusual concentrations of star-forming activity. Spectroscopic analysis refuted it. The spectral signatures of little red dots did not match starburst galaxies. The chemistry was wrong. The hypothesis was abandoned. The second explanation, which gained traction through 2023 and into 2024, was that little red dots were active galactic nuclei, galaxies whose central supermassive black holes were actively consuming surrounding gas and radiating enormous amounts of energy across the electromagnetic spectrum. Active galactic nuclei are among the brightest objects in the universe. They are also reliable X-ray sources. When gas spirals into a black hole and forms a hot accretion disk, the extreme temperatures and magnetic fields involved produce X-ray radiation that travels outward through whatever surrounds the black hole. If little red dots were active galactic nuclei, they should appear in X-ray surveys. Of the 341 catalogued objects, exactly 2 were detected in X-rays. 2. That is not a marginal result. That is a refutation. The hypothesis was abandoned. The third explanation, emerging in September of 2025, was a theoretical proposal that little red dots might be a class of object called black hole stars, a configuration in which a black hole forms the gravitational core of an enormous ball of gas, powering the whole structure from inside rather than through conventional stellar nuclear fusion. The hypothesis grew partly from the analysis of a specific little red dot called the Cliff, discovered through a survey program called Rubies, and notable for an extraordinarily steep spectral feature called a Balmer break, a signature that no existing model of starburst galaxies or conventional active galactic nuclei could reproduce. The black hole star hypothesis offered a way to explain the anomaly. It remained unconfirmed. Then, January 2026 arrived, and the field had a new problem on its hands. In the same week, 2 research teams on opposite sides of the Atlantic published papers that offered, simultaneously and independently, completely different answers to what little red dots were, and both papers claimed to explain everything the observations had shown. The first paper appeared in Nature on the 14th of January from researchers at the Cosmic Dawn Center at the University of Copenhagen. The team, led by Professor Darach Watson and including lead author Vadim Rusakov, had analyzed the highest quality Webb spectra of little red dots and found something that previous analyses had missed. The broad emission lines that had led earlier researchers to infer the presence of massive, fast-spinning black holes were not, the Copenhagen team argued, being broadened by the Doppler motion of gas orbiting a black hole at all. Instead, the lines were being broadened by electron scattering, a process in which photons bounce repeatedly off electrons in a dense surrounding medium, having their wavelengths shifted in random directions, producing a characteristic pattern in the spectrum that mimics the appearance of Doppler broadening, but is caused by something entirely different. The little red dots in this picture were young black holes wrapped in extraordinarily dense cocoons of ionized gas, feeding on that gas and growing larger, with the heat generated by that consumption glowing through the cocoon to produce the intense red color. The same dense cocoon that scattered the emission lines also absorbed the X-rays, explaining why almost none had been detected. Watson described the objects as far less massive than previous estimates had implied, between 100,000 and 10 million solar masses, rather than the billions some analyses had suggested. "We do not need," he said, "to invoke completely new types of events to explain them." The second paper, published in the Astrophysical Journal in February by researchers at the Harvard-Smithsonian Center for Astrophysics, arrived at a completely different conclusion. The team, led by Devesh Nandal with co-author Avi Loeb, had built detailed physical models of a class of object that has long been theorized but never directly observed: metal-free supermassive stars, objects of approximately 1 million solar masses formed in the first moments of cosmic history, from the purely primordial mixture of hydrogen and helium that existed before any heavy elements had been forged by stellar nucleosynthesis. When Nandal and Loeb ran their models and compared the predicted spectral signatures to the observed properties of little red dots, the match was striking. The redness, the compactness, the luminosity, the absence of heavy element lines, the shape of the spectral energy distribution, all of it consistent with stars of this type, enormous and short-lived, burning through their fuel in a few million years before collapsing into the first black hole seeds. Nandal described the finding as watching some of those seeds being born in real time. 2 papers, 2 institutions, 2 entirely different objects that the little red dots were claimed to be, published within weeks of each other, neither refuted by the other. No consensus. Consider what that moment represents, not just scientifically, but as a picture of how knowledge actually accumulates at the frontier. Hundreds of researchers across dozens of institutions had devoted years to these objects. Graduate students had written dissertations about them. Observing time on the most expensive scientific instrument ever built had been allocated to them. 3.5 years of increasingly confident wrong answers, each one narrowing the search space, none of them settling the question. And then, at the point where 2 of the most credible answers the field had yet produced arrived simultaneously, they contradicted each other. The scientific process is working exactly as it should. Each failed hypothesis eliminated a possibility. Each elimination brought the field closer to whatever the truth is. But the objects themselves have refused, for 3 years running, to be neatly categorized. That is what a genuinely new phenomenon looks like in real time. Not a press release. Not a clean discovery with a single correct answer waiting at the end of a tidy chain of evidence. This, accumulating wrong answers and 2 contradictory right ones, while the objects themselves continue to sit in the data, red and compact and unexplained, waiting. Buried beneath every equation cosmologists use to describe the universe is an assumption so fundamental that most textbooks do not flag it as an assumption at all. It is treated as a given, a background condition on which the entire formal structure of modern cosmology rests. It is called the cosmological principle. The cosmological principle states that the universe, at large enough scales, is the same everywhere and in every direction. Isotropic, looking identical no matter which way you point your telescope. Homogeneous, having the same average properties at every location, with no special places, no preferred axes, no built-in orientations inherited from the beginning. The universe, according to this principle, has no handedness. There is no up, there is no left. Statistically, it is smooth. This is not merely a philosophical preference. The equations that describe cosmic expansion, the Friedmann equations that underlie all of lambda cold dark matter, are derived from Einstein's general relativity under the assumption of isotropy and homogeneity. Without that assumption, the equations cannot be solved in their current form. The cosmological principle is not one ingredient among many. It is the mathematical license that allows any of the other calculations to be made. If the universe is not actually isotropic, if it has preferred directions or large-scale asymmetries, then the equations are being applied to a universe they were not designed to describe. Every conclusion drawn from them carries that error forward. The principle has never been directly verified at the largest scales. It is supported by the general smoothness of the cosmic microwave background, which looks roughly uniform across the sky, and by the large-scale distribution of galaxies, which appears statistically consistent with homogeneity when averaged across sufficiently large volumes. But the support is indirect, and the scales at which the principle is assumed to hold are scales at which direct verification remains difficult. Galaxies spin. Like weather systems and planets, they rotate, some clockwise when viewed from a particular direction, some counterclockwise. In a universe with no preferred axis and no directional memory of its initial conditions, those spins should be distributed randomly across the sky. The ratio of clockwise rotating galaxies to counterclockwise rotating galaxies in any sufficiently large and unbiased sample should be approximately 1:1. Lambda, cold dark matter, is unambiguous on this point. In 2025, Lior Shamir, an associate professor of computer science at Kansas State University, published an analysis in the monthly notices of the Royal Astronomical Society that produced a different ratio. Shamir had applied computer-based quantitative methods to images of 263 spiral galaxies in the JD's survey. The same deep field data that had yielded JD's GSZ 14-0 and the galaxy rotation direction measurements that earlier surveys had hinted at. His algorithm analyzed the curvature of the spiral arms in each galaxy to determine its rotation direction as seen from Earth. The result was 158 galaxies rotating clockwise and 105 rotating counterclockwise, approximately 2:1. The one-tailed binomial probability of observing an asymmetry this large by chance in a sample of this size, if the underlying distribution were truly random, is approximately 0.07%. That is not a large sample, and Shamir acknowledged this explicitly. He also noted two possible explanations that did not require a violation of the cosmological principle. The JD's field sits near the southern galactic pole, and the Milky Way's own rotational velocity relative to the external universe could, through the Doppler effect, subtly alter the apparent brightness of galaxies depending on whether they rotate in the same direction as or against our own motion, potentially biasing the counts. This is a legitimate alternative explanation, and it has not been ruled out. What lends the finding greater weight is that it does not stand alone. Shamir noted that the same asymmetry, a higher number of clockwise rotating galaxies in the same region of sky, had appeared previously in large datasets collected by the Sloan Digital Sky Survey, the Pan-STARRS Observatory, and the Hubble Space Telescope. The magnitude of the asymmetry appears across all of these datasets to increase at higher redshifts. That is, further back in cosmic time, the directional bias looks larger. Independent replication by other research groups has not yet been achieved, and the finding remains contested. It should be treated with the caution that contested findings require. But the question it raises is one that cosmology cannot dismiss by pointing to the smallness of the sample alone. If the asymmetry is real and not an artifact of the Milky Way's motion or some other observational bias, if the early universe genuinely has a preference for one rotation direction over the other, the implications for the cosmological principle are severe. A universe that rotates preferentially clockwise is a universe that remembers something from its beginning. It inherited a directional bias from the conditions in which it was born. It has, in the most literal sense, a handedness. A universe with a handedness is not the universe that lambda cold dark matter was built to describe. Every inference drawn from the assumption of isotropy, including the derivation of the Hubble constant from the cosmic microwave background, including the entire machinery of structure formation models, including every extrapolation from a local measurement to a universal conclusion, rests on a foundation that, if the cosmological principle is violated, was never as solid as the field believed. The rotation asymmetry is not the only data point that pushes in this direction. The Hercules Corona Borealis Great Wall is a structure of galaxies and galaxy clusters spanning roughly 10 billion light-years, larger than any structure that simulations built on lambda cold dark matter can produce. The South Pole cold spot in the cosmic microwave background, a region of the sky anomalously cold compared to the surrounding radiation, has resisted explanation for decades. Features in the microwave background known as the axis of evil, an alignment of large-scale patterns with the plane of the solar system, have been debated in the literature since they were first identified. Each of these anomalies taken alone is manageable. Taken together, they form a pattern. A universe that may have preferred directions, preferred scales, preferred asymmetries that a perfectly uniform cosmos should not possess. No one has declared the cosmological principle broken. The field is not ready to take that step. But the question is being asked with increasing seriousness by researchers who, 5 years ago, would not have entertained it. And the possibility that it is asking, whether the license to extrapolate from one region of the sky to the whole universe was valid in the first place, touches something far more fundamental than any individual anomaly. If the framework itself contains a flaw, then the anomalies it produces are not problems to be patched. They are symptoms. 40 years is a long time to be right, while everyone treats you as wrong. In January of 1983, Mordechai Milgram, a physicist at the Weizmann Institute of Science in Israel, published 3 papers simultaneously in the Astrophysical Journal. Together, those papers proposed something that the mainstream of physics was not prepared to take seriously: a modification of Newton's second law of motion that applied only in regimes of extremely low acceleration, regimes that exist in the outer regions of galaxies, far from their dense luminous cores, but nowhere in our solar system or in any laboratory environment where physics had been tested. The problem Milgram was trying to solve was real and uncontested. Galaxies rotate at speeds that should, by any standard application of gravitational physics to the mass that can be seen in them, tear them apart. The outer stars and gas in a spiral galaxy move far faster than they have any right to, given the amount of visible matter whose gravity is supposedly holding them in orbit. This discrepancy had been accumulating in the observational record since the 1970s, and by 1983, it was undeniable. Something was wrong with the picture. The dominant explanation, which would eventually become the cold dark matter, half of lambda cold dark matter, was that vast halos of invisible mass surround every galaxy. Dark matter, detectable only through its gravitational effects, providing the additional pull that keeps the outer stars from flying free. Milgram proposed something different. Instead of adding invisible matter, he proposed modifying the law of gravity itself. Specifically, he argued that below a certain threshold of acceleration, a universal constant now designated as Milgram's acceleration constant, the strength of gravity does not fall off with distance the way Newton's inverse square law predicts. It falls off more slowly. The result, at the low accelerations experienced by stars in the outer regions of galaxies, the gravitational pull they feel is stronger than standard physics says it should be, without any dark matter required. The mainstream response was swift and comprehensive in its dismissal. Lambda cold dark matter was performing extraordinarily well. It reproduced the cosmic microwave background. It generated the large-scale structure of the universe. It explained galaxy clusters. Dark matter was the preferred explanation, and Milgram's framework was consigned to the scientific margins, cited mainly by a small community of researchers who kept refining it while the rest of the field moved on. For 4 decades, modified Newtonian dynamics was treated not as a serious contender, but as a persistent curiosity that worked for galaxy rotation curves and failed everywhere else. Stacy McGaw at Case Western Reserve University was among the researchers who never stopped working on it. His group spent those decades testing the framework against observational data. refining its predictions, and building the case that the tight relationship between the visible matter in a galaxy and its rotational velocity, a relationship that falls out naturally from Milgram's modification, but requires considerable fine-tuning to reproduce in dark matter simulations, was pointing towards something real. It was not a comfortable position to occupy. Funding was difficult. Collaboration opportunities were limited. The prestige machinery of the field pointed elsewhere. Then, in November 2024, Magor and his colleagues published a paper in the Astrophysical Journal titled Accelerated Structure Formation: The Early Emergence of Massive Galaxies and Clusters of Galaxies. The argument they made was specific and pointed. The observations from the James Webb Space Telescope, the massive early galaxies that had been appearing in the data since the first images, the objects that were too large and too mature for the age of the universe at which they existed, were consistent with predictions that Magor and his colleagues had made in 1998, under a framework informed by Milgram's approach to gravity. The same predictions were not consistent with what lambda cold dark matter's hierarchical structure formation scenario said should be there. Magor's own summary of the situation was blunt. The expectation had been, he said, that every large galaxy we see in the nearby universe would have started from small pieces, the bottom-up assembly that the cold dark matter model requires. That was not what Webb was showing, and the bottom line, in his words, was, "I told you so." He was raised, he added, to think that saying so was rude. But that, he said, is the whole point of the scientific method. Make predictions, then check which ones come true. What modified Newtonian dynamics gets right is notable. It naturally predicts the rapid early assembly of large structures. It generates a tight coupling between visible matter and gravitational behavior that dark matter simulations struggle to reproduce. Some features of the galaxy rotation asymmetry data that Shamir analyzed are consistent with the framework's expectations, and it makes all of these predictions without invoking any matter that has never been directly detected. What it does not explain is equally notable. Galaxy clusters, enormous gravitationally bound systems containing hundreds or thousands of galaxies, do not behave the way the framework predicts without invoking some additional mass. The cosmic microwave background, which lambda cold dark matter reproduces with extraordinary precision, is harder to match under modified Newtonian dynamics in its current forms. The framework has not yet produced a fully relativistic formulation that can compete with the standard model on the full range of cosmological tests. It is not a complete theory of the universe. It remains, in important respects, an incomplete one. The James Webb Space Telescope did not vindicate modified Newtonian dynamics. That would require a much more comprehensive accounting than JWST alone can provide. What Webb did was force cosmology to stop pretending the alternative did not exist. Researchers who had spent decades being told they were pursuing a dead end are now receiving invitations to conferences and offers of collaboration. Their predictions are being tested against data with genuine openness rather than institutional indifference. The dismissal is over. What does it mean when an alternative that the mainstream ignored for 40 years turns out to have been pointing towards something real? It means the mainstream was wrong to ignore it. Not necessarily wrong in its conclusions. Lambda cold dark matter may yet absorb the challenge and survive, but wrong in its method. The prestige hierarchies, the funding structures, the publication incentives that collectively decide which ideas receive resources and which are starved of attention. Those mechanisms failed for 4 decades. The ideas survived anyway, kept alive at the edges of the field by researchers willing to work outside the consensus. They waited for data that would force the center to listen. The data arrived, and the center is listening now. The challenge from modified Newtonian dynamics came from outside the standard model. The challenge we turn to now came from inside, from theorists who accepted lambda cold dark matter's framework and set about finding a way to repair it. The most prominent repair proposal had a name, a tightly reasoned logic, and an uncomfortable question buried at its center that its own proponents could not quite answer. The question is this: at what point does fixing a model become abandoning it? The Hubble tension demanded a response. Two precise measurements of the same fundamental quantity disagreed at a level that could not be explained by error alone. Something in the physics had to account for the gap, and the theoretical community turned itself toward the problem with genuine urgency. Among the responses, the one that gained the most traction was proposed by Mark Kamiankowski of Johns Hopkins University, working with colleagues in the years leading into the 2020s. The proposal was called early dark energy. The logic went like this. The Hubble tension arises because the expansion rate inferred from the cosmic microwave background, from the earliest light in the universe, emitted about 380,000 years after the Big Bang, disagrees with the expansion rate measured from nearby galaxies today. If something had briefly altered the expansion rate in that early epoch, the microwave background calculations would yield a different, slightly higher Hubble constant, one that could reconcile with the local measurement. Early dark energy is that something, a brief additional energy component that existed in the universe's first 380,000 years, slightly accelerating expansion beyond what the standard model predicts, and then disappeared completely, leaving no further trace. The mathematics is coherent. A correctly specified burst of early energy in the right epoch shifts the microwave background measurements in precisely the direction needed. The tension dissolves. The model survives. Has anyone detected early dark energy? No, not once, in any instrument, in any observation. There is no direct evidence that it exists. There is no confirmed observational fingerprint, no secondary effect on the microwave background that its presence would uniquely produce, beyond the adjustment to the expansion rate it was designed to explain. Early dark energy is inferred solely from the gap between two numbers that refuse to agree. It was introduced because the equation produces the wrong answer without it. This is not disqualifying on its own. Science is full of entities that were inferred before they were detected. The existence of Neptune was inferred from anomalies in the orbit of Uranus decades before anyone pointed a telescope at where it had to be. The existence of the Higgs boson was inferred from the structure of the standard model of particle physics for decades before the Large Hadron Collider confirmed it. Prediction before detection is not a flaw. It is how the process works. The discomfort with early dark energy runs deeper than the fact that it has not been detected. To feel that discomfort, you need to look at what lambda cold dark matter already requires. 5% of everything that exists is ordinary matter. Atoms, molecules, the substance of stars and planets, and every living thing. Everything you can see, touch, or measure directly. 5%. 27% is cold, dark matter, invisible to light. Never directly detected in any laboratory on Earth despite decades of underground experiments designed specifically to catch it and multiple generations of particle accelerators searching for it. Its existence is inferred from gravitational effects, galaxy rotation curves, gravitational lensing, the large-scale distribution of cosmic structure. The indirect evidence is genuine and strong. The thing itself has never been directly observed. 68% is dark energy, a property of space itself, inferred entirely from the fact that the expansion of the universe is accelerating. Its physical nature is completely unknown. It may be a cosmological constant, a fixed energy density inherent to empty space. It may be a dynamic field that changes over time. Nobody knows. Preliminary data from the Dark Energy Spectroscopic Instrument Survey, gathered across 2024 and 2025, suggested that dark energy may be weakening, evolving toward lower values as cosmic time progresses. If confirmed, that would alter the late universe expansion history and might, from the other direction, help close the Hubble tension. As of early 2026, that result was still preliminary and had not been independently confirmed. Now add early dark energy. The model would require 3 separate undetected components, 3 invisible pillars holding up the architecture of the universe, each one individually defensible, each one resting on real indirect evidence. Together, constituting a theoretical framework that describes the cosmos almost entirely through ingredients that cannot be directly characterized. Kamionkowski and his colleagues are not naive about this. They know the epistemological weight of what they have proposed. In workshops and conference rooms, the question comes up with regularity: is this still science the hard way? Or is this something more comfortable and less honest? A scientific model is powerful precisely because it makes predictions that can be tested and, in principle, proven wrong. A model that can accommodate any observation by adding additional invisible components is no longer making predictions in the most meaningful sense. It is making adjustments. Those two activities look similar from the outside. From the inside, they are entirely different enterprises. The field has not reached the point where the patches outnumber the original structure. Lambda cold dark matter still generates concrete, testable predictions across a wide range of phenomena, and most of them remain in excellent agreement with observation. The falsifiability concern is a warning, not yet a verdict. But the question has been asked, and it has not gone away. Patching a model is legitimate science until it isn't. The line between the two is not always visible until you are some distance past it. And the field is watching carefully to see which side of that line the Hubble tension ultimately pushes it toward. Both modified Newtonian dynamics and early dark energy are responses to the same accumulating pressure. But neither of them begins at the very beginning, at the first fraction of a second after the Big Bang, when the entire universe was a hot, violently uneven place, where the seeds of everything that came after were being planted. One hypothesis does begin there, and Webb keeps finding objects that it, alone among the alternatives, offers any hope of explaining. The standard account of how black holes form runs through stellar death. A massive star, something many times heavier than our Sun, exhausts the nuclear fuel in its core after millions of years of burning. Without the outward pressure of fusion to hold it up, gravity wins. The core collapses. If the star is massive enough, the collapse cannot be stopped by any known force, and a black hole forms at the center, a region of space-time so deeply curved that nothing, not even light, can escape once it crosses the boundary. This process is well understood. It has been observed indirectly across thousands of stars in the universe, and it fits comfortably within the framework of lambda cold dark matter's timeline for how structure assembled itself after the Big Bang. The earliest black holes, on this account, formed from the deaths of the first massive stars, objects that began their lives roughly 200 to 400 million years after the Big Bang and lived for a few million years before collapsing. From those seeds, subsequent black holes grew by consuming surrounding gas and by merging with one another across billions of years of cosmic history, eventually producing the supermassive black holes that sit at the centers of most large galaxies today, including the one at the center of the Milky Way. Slow accumulation over vast timescales. The model was clear. James Webb keeps finding black holes that have not read the model. In galaxy after galaxy in the early universe, the telescope has detected evidence of supermassive black holes that contain hundreds of millions or even billions of solar masses, already fully assembled when the universe was only a few hundred million years old. The stellar evolution pathway cannot produce objects that massive that quickly. There is simply not enough time for enough stars to have been born, to have lived out their stellar lifetimes, to have collapsed, and for the resulting black holes to have grown through ordinary accretion to the masses being observed. The numbers do not work. Something else must have seeded these objects, or the pathway to their formation is entirely different from the one the standard model describes. One hypothesis offers a radically different origin story. In the first fractions of a second after the Big Bang, the universe was not smooth. It was violently uneven, shot through with regions of extreme density fluctuating against regions of relative emptiness. The quantum fluctuations of its earliest moments, written at enormous scales across the newborn cosmos. The hypothesis of primordial black holes proposes that wherever those density fluctuations exceeded a critical threshold, Gravity could have overwhelmed the outward pressure of the expanding newborn universe and collapsed those regions directly into black holes. No stars required, no stellar evolution, no waiting. The mass range of objects that could have formed this way spans an enormous spectrum. Small density fluctuations would produce primordial black holes of very low mass, objects less massive than a single asteroid. Larger density fluctuations, arising from rarer and more extreme overdense regions, could produce primordial black holes carrying millions of solar masses from the very moment of their creation. Objects of this kind, seeded before any star existed, would have served from the beginning as gravitational attractors, pulling in surrounding gas, compressing it, triggering star formation at rates that ordinary dark matter halos could not generate. The result would be exactly the kind of early, massive, chemically complex galaxies that Webb keeps finding. Structures that assembled far faster than hierarchical formation models allow, built around seeds that arrived not at the end of stellar evolution, but at the very start of cosmic history. Avi Loeb at Harvard has been among the more prominent voices urging the field to take this hypothesis seriously as an observational target rather than a theoretical curiosity. The case for doing so is not based on direct detection. No primordial black hole has ever been confirmed, but on the accumulation of objects that the standard formation pathway cannot plausibly explain, and on the absence of any observation that has definitively closed the relevant mass windows. Gravitational microlensing surveys, observations that watch for the temporary brightening of background stars as a compact dark object passes in front of them, and analysis of the cosmic microwave background have already constrained the primordial black hole hypothesis across many mass ranges. In some windows, the constraints are tight enough to rule out primordial black holes as the dominant component of dark matter. In others, the constraints are weaker, and meaningful populations of primordial black holes remain consistent with the data. The hypothesis is genuinely unconfirmed, but equally, no observation has conclusively refuted it in the mass ranges most relevant to the objects Webb is finding. And given that the telescope is producing evidence of early supermassive black holes that no other current hypothesis explains cleanly, the idea that the universe seeded itself with black holes before the first star ignited has moved from the margins of speculation to the edge of serious contention. If primordial black holes in the relevant mass ranges do exist, what they mean for our picture of the universe is profound. It would mean the universe arrived pre-structured, pre-wired with gravitational seeds from its very first moments, objects born from the turbulence of the Big Bang itself, rather than from the long, slow process of stellar evolution. The architecture of everything visible, every galaxy, every cluster, every filament spanning the cosmic web, would trace back not to the patient accretion of matter over billions of years, but to density fluctuations in the first fraction of a second of existence. That is either an answer or the opening of a vastly deeper question. And the two are not necessarily distinguishable yet. All of the anomalies, the proposed explanations, the 40-year alternatives brought in from the cold, they have been happening in offices and observatories and conference rooms. They have been happening to people. And there is one person whose account of what it feels like to live through this moment is worth pausing for. In 2023, a professor of astronomy at the University of Kansas said something that spread through the cosmology community and landed differently depending on who heard it. Alison Kirkpatrick had spent her career studying galaxies in the early universe. She had been trained in the framework of lambda cold dark matter. She had taught it to her students. She had built her research program around its predictions, designed her observations to test its specific claims, written grant proposals citing its well-established success, and mentored graduate students who were planning their own careers inside the same edifice. She was, in that sense, entirely representative of a generation of cosmologists who had entered the field when the standard model felt solid, who had devoted the most productive years of their working lives to its elaboration, and who were now watching its foundations develop cracks. What Kirkpatrick said was this: right now, she told an interviewer, she found herself lying awake at 3 in the morning, wondering if everything she had ever done was wrong. For a non-specialist, that sentence reads as a moment of professional self-doubt, vivid and honest, but essentially relatable, the kind of late-night anxiety that most people have experienced in some form. For anyone who understands what it takes to build a career in theoretical science, it reads as something different, something closer to vertigo. Consider what it took to reach the point where Kirkpatrick was lying awake. Years of graduate school, learning the mathematics and the observational methods that underpin the Standard Model well enough to contribute to it. A doctoral dissertation, months or years of focused work, producing an original contribution to knowledge inside a specific framework. Postdoctoral positions, one against competition from dozens of other candidates, each one requiring a demonstrated fluency with the model's predictions and the skill to extend them. A faculty appointment at a university, one against fiercer competition still, requiring the production of a research program coherent and ambitious enough to persuade a hiring committee that you were worth the investment. Courses designed around the model, graduate students brought into the field through your teaching, starting their own careers in the same conceptual framework you had been building inside for a decade. Papers published, grant proposals funded, a professional identity constructed, piece by piece, around a particular picture of how the universe works. And then the data starts saying the picture might be wrong. The weight of that is real. It carries grief. The loss of certainty in something you have staked years on is a genuine form of loss, not merely intellectual discomfort. Some of that grief is ego. Yes, the ego that comes with any significant commitment to a position and the disorientation of having that position challenged. But much of it is something more elemental. The disorientation of finding that the map you have been using to navigate does not match the territory. The map was carefully made. It was tested against every landmark you could reach. It worked for years with impressive consistency. And now new instruments are revealing that some of the landmarks were not where you marked them, and some of the terrain was not the shape you drew. Kirkpatrick has also spoken about something else she encountered when she sat with the discomfort rather than retreating from it. Something she did not expect. Alongside the anxiety, not replacing it, but sitting with it. Something that felt more like exhilaration. Because if the map is wrong, the territory is more interesting than anyone knew. The career you thought you had, exploring the known corners of a mostly understood universe, filling in the details of a story already largely told, turns out to be something far more open and far more alive. The questions you thought were answered are not answered. The things you thought were settled are not settled. The scientific enterprise, which can sometimes feel like a long process of confirmation, has abruptly become something much stranger and much more exciting, a genuine confrontation with the unknown. That duality, grief and exhilaration coexisting, neither cancelling the other, is the most honest account of what it feels like to be a working cosmologist in the mid-2020s. There is another dimension to this that is easy to miss. The engineers who first proposed the James Webb Space Telescope in 1996 imagined it would confirm and extend the Standard Model. Some of them had died before its first light images arrived. Some had retired before the anomalies began accumulating. The telescope took 25 years from proposal to launch, and the people who conceived it did not know what it would actually find. They hoped, they modeled, they prepared. But the universe had not consulted the models, and the graduate students who enrolled in cosmology programs around 2019, drawn by the prospect of working with Webb data, were told that the framework was mature and their job would be to fill in the details. They are now, a handful of years into their training, sitting with data that their dissertations did not predict. They are the generation that may have to rebuild rather than extend. They did not sign up for that. They are discovering, in real time, that it may be the more significant work. Science works correctly when it produces exactly this kind of discomfort. The discomfort is not a failure of the system. It is the system functioning as designed, generating data that challenges assumptions, forcing revision, creating the productive uncertainty that precedes genuine understanding. It is still frightening to wake at 3 in the morning and wonder whether your map of reality needs to be redrawn. That fear is real, and it belongs to an entire generation of researchers living through the most significant revision of cosmological understanding in decades. Kirkpatrick has not stopped working. Nobody has. The telescope is still up there, and on the ground, fully assembled and waiting for launch, is the instrument that was built specifically to answer the questions Webb has raised. James Webb sees a postage stamp. What comes next sees a poster. The Nancy Grace Roman Space Telescope was conceived on a different philosophy from its predecessor. Where Webb was designed to look extraordinarily deep into small patches of sky, Roman was built to look wide, to cover enormous swathes of the observable universe with the kind of sensitivity and resolution that only a space-based observatory can achieve. Its primary imaging instrument has a field of view 100 times larger than Webb's. A single Roman exposure will contain as much sky as roughly 200 comparable Hubble images. In its first 5 years, the telescope is expected to catalogue over 1 billion galaxies. The telescope is named after Nancy Grace Roman, who served as NASA's first chief astronomer and its first female executive, beginning in 1959. Roman spent her career building the institutional and technical infrastructure that made space astronomy possible, often working against the assumption that broad sky surveys were less scientifically valuable than narrow-pointed observations. She argued consistently that understanding the universe required seeing its large-scale structure, not just its deepest individual corners. The philosophy she advocated over decades is now literally built into the design of the telescope that carries her name. On the 25th of November 2025, engineers at NASA's Goddard Space Flight Center completed the assembly of the Roman Space Telescope, joining its 2 major segments in the facility's largest clean room. The telescope was on schedule and under budget. It was preparing to move to Kennedy Space Center for launch preparations in the summer of 2026. NASA was working toward a launch as early as the autumn of that year, with a firm commitment date no later than May 2027. A SpaceX Falcon Heavy would send it to the Sun-Earth Lagrange point 2, the same gravitational equilibrium point that Webb occupies, roughly 1 million miles from Earth. None of this was inevitable. In April 2025, the Trump administration's budget proposal for the following fiscal year included a cut to Roman's development funding from approximately $400 million to $156 million. The reduction was so severe that experts across the astronomical community described it as a de facto cancellation. The telescope was fully built, it was on schedule and under budget, and the proposal would have cut the funding needed to complete its final testing and prepare it for launch. Casey Dreyer of the Planetary Society called the proposed cuts an extinction-level event for NASA science. Missions that had already been paid for, already launched, already returning results were on the chopping block alongside Roman. The scale of the proposed reductions was the largest in NASA's history as a percentage of the science budget. Congress rejected the cuts. In January 2026, the fiscal year 2026 budget legislation explicitly protected Roman's funding, including language that prevented the administration from redirecting the money elsewhere. The telescope survived. It was ahead of schedule. But the episode served as a reminder that the science we discuss as if it were inevitable, the data that is already reshaping cosmology, came within one legislative decision of not existing. That echo of JWST's own history is not incidental. Webb spent nearly a decade in genuine danger of cancellation. Multiple budget battles, a nearly complete termination in 2011, delays that stretched its timeline by 14 years past the original target. It survived because enough people, at enough critical moments, chose to protect it. Roman survived its own version of that gauntlet in a compressed and more dramatic form. The knowledge that these instruments produce was never guaranteed. It was fought for. What Roman will do with the access it survives to obtain is specific and consequential. On the Hubble tension, Roman will measure the expansion rate of the universe using at least 3 entirely independent methods simultaneously. Weak gravitational lensing, the clustering of galaxies across cosmic time, and the brightness of Type 1a supernovae across a sample far larger than any previous survey. If the tension between the early universe and local universe measurements is a real feature of the cosmos, rather than a statistical artifact of limited samples, Roman's combined measurement will make that definitive and characterize the discrepancy with a precision that current data cannot approach. On the early galaxy problem, every anomalous early galaxy that Webb has found sits inside a tiny patch of sky. The current evidence for overabundant early massive galaxies rests on observations of a combined area that is a negligible fraction of the total observable sky. Roman will survey millions of galaxies across the same redshift ranges that have been producing Webb's anomalies. If the excess of early massive galaxies is a real feature of the universe, it will be unambiguous in Roman's data. If it is a sampling accident, an overdense region that Webb happened to look at, that too will be unambiguous. There is no reading around a survey of hundreds of millions of galaxies. On dark energy, if the component driving the universe's accelerating expansion is a cosmological constant, a fixed property of empty space, unchanging across time, its influence on the rate of cosmic expansion should be identical at all epochs. If it is instead a dynamic field that evolves, Roman will detect that evolution across the billions of years of cosmic history its survey spans. The preliminary DESI data, suggesting dark energy may be weakening, will either be confirmed or refuted by observations with far greater statistical power. Roman will not answer every question that Webb has raised. It cannot resolve the cosmological principle question alone, and it will not directly detect dark matter or primordial black holes. What it will do is determine whether the picture Webb has assembled is a portrait of the universe or a portrait of one unusual corner of it. Either answer resolves questions that are currently worth decades of theoretical labor. Julie McEnery, Roman's senior project scientist at Goddard, described the telescope's potential in terms that matched the moment. With its construction complete, she said, "We are poised at the brink of unfathomable scientific discovery." Roman is the next conversation, and it will be a conversation the universe has to participate in directly. Step back from the individual anomalies for a moment. The oxygen in a galaxy too young to have it. The hundreds of millions of galaxies 182 times more abundant than predicted. The signal through the fog. The expansion rate that disagrees with itself. The compact red objects that 4 years of research have produced 2 contradictory explanations for in the same week. The possible handedness of the universe. Set all of that aside and ask the question that sits behind every one of them. How do great theories actually fall? The honest answer, when you look at the historical record carefully, is slowly and then suddenly, and almost never through a single devastating experiment. The pattern repeats across the history of physics with a regularity that should give anyone examining the current moment either comfort or concern, depending on how they read it. Consider Newtonian gravity. At the height of its dominance, Newton's mechanics was the most successful scientific theory that had ever existed. It predicted planetary orbits with extraordinary precision. It explained the tides. It launched the industrial age and sent navigators around the globe. It was, by any measure of practical verification, unassailable. Then astronomers looked at the planet closest to our star and found a discrepancy. Mercury's orbit traces an ellipse that slowly rotates around the Sun, and the rate at which it rotates exceeded what Newton's equations could account for by 43 arcseconds per century. 43 arcseconds. A number so small it sounds like a rounding error, but it was real, reproducible, and could not be made to go away. It took 40 years of accumulated discomfort before Einstein's general theory of relativity arrived to explain it. Consider the static universe. Before Edwin Hubble's redshift measurements in the 1920s, the dominant assumption across cosmology was that the cosmos existed in a permanent steady state, neither expanding nor contracting. Einstein himself installed a term into his own field equations, specifically to prevent the universe from expanding, because an expanding universe was conceptually uncomfortable to him. Then Hubble published. The universe was not static. The static model did not slowly yield and negotiate. It collapsed overnight. Consider the steady-state model of the 1950s. Fred Hoyle, one of the most brilliant physicists of his generation, argued that the universe had no beginning, that matter was continuously created to maintain a constant average density as space expanded. The model had genuine predictive power and genuine elegance. It died in 1965 when Arno Penzias and Robert Wilson, working with a radio antenna in New Jersey, detected a faint microwave signal arriving uniformly from every direction in the sky. It was the afterglow of the Big Bang, radiation left over from a hot, dense beginning that steady-state cosmology had no room for. The pattern across all three cases is the same. The anomalies were present for years, sometimes decades, before the paradigm shifted. The defenders of the old model were not stupid or resistant to evidence. They were often the most rigorous scientists in the field, pressing their case with legitimate methodological care. The shift came when the weight of unexplained observations reached a threshold that no patch could address, and when a framework arrived that could account for all of it, rather than just the things the old model had always explained. Lambda cold dark matter has survived serious challenges before. The missing satellites problem, the too big to fail problem, various tensions between simulations and observations that were resolved through better modeling of how gas, stars, and feedback processes behave inside dark matter halos. The model adapted, the model endured. History says it will likely endure again. But history also says that when anomalies are varied enough, consistent enough, and resistant enough to individual explanation, the model that survives a confrontation of this scale does so by becoming something different from what it was. Not failed, but transformed. The field inside cosmology, as of early 2026, is not unified. It is not quietly confident. There is a real and widening distribution of opinion about what the Webb findings mean and where the standard model stands. One group, still probably the majority, believes lambda cold dark matter will survive through improvements in simulation fidelity and a better treatment of stellar feedback and galaxy formation physics. Their argument is not complacency. It is the track record of a model that has absorbed challenges before and emerged stronger. A second group believes the model requires fundamental revision rather than incremental adjustment, that the number, variety, and consistency of the anomalies point to something wrong with the core assumptions, not merely with the secondary parameters. A third group, smaller but growing, has started using a word that mainstream cosmology has historically been reluctant to invoke: paradigm shift. These researchers argue that the accumulation of Webb anomalies, taken together with the Hubble tension and the large-scale structure discrepancies, points toward an incompleteness in the current model that cannot be patched, only replaced. What is striking is the size of the group that occupies none of these positions definitively. A large fraction of working cosmologists, when asked privately, do not know which camp is right. They are continuing to publish. They are continuing to work within lambda cold dark matter because it has the tools, the predictions, and the community. But the certainty that characterized the field in the years after the Planck satellite's cosmic microwave background maps arrived, that sense of a mostly finished picture being filled in around the edges, has quietly and significantly eroded. One senior cosmologist, speaking at a workshop in 2024, put it with the directness that private settings sometimes allow. The data, he said, is telling us something. We do not agree on what. That is not a crisis, it is a condition. And it is the specific condition that precedes genuine understanding. The honest summary of where cosmology stands in early 2026 is this: lambda cold dark matter's predictions about the composition of the universe the proportions of dark matter and dark energy, the large-scale distribution of structure across the cosmic web, remain in good agreement with most available data. The problems are specific. They are concentrated not randomly across the model, but in the places where its assumptions are most fundamental. The timeline of early galaxy formation, the rate of cosmic expansion, the chemical maturity of the earliest objects, the schedule of reionization, the possible directional bias in the universe's deepest structures. These are not peripheral concerns. They are questions about when and how the first things formed, and about whether the universe that contains us is the uniform, directionless cosmos that the standard equations assume. What science at a threshold actually looks like is not a press release. It is not a clean discovery with a Nobel Prize waiting at the end of a tidy chain of evidence. It looks like this: accumulating anomalies, competing explanations, simultaneous contradictory papers about the same population of objects, genuinely uncertain researchers working inside a framework they are no longer certain is the right one. The confusion is not a dead end. Every wrong answer narrows the search space. Every anomaly is an arrow pointing somewhere new. The discomfort is the process working. Up there, nearly 1 million miles from Earth, the gold mirror is still turning, cooling itself to temperatures colder than the space between most stars, collecting photons that left their sources hundreds of millions and billions of years ago and have been traveling toward a mirror that did not exist when their journey began, sending home data that no one fully understands yet. And down here, a generation of researchers, some of them lying awake at 3 in the morning, wondering if everything they have ever done is wrong. Some of them feeling something closer to exhilaration at the thought that the map they were handed may need to be redrawn, are trying to read what those photons say. Science is not the accumulation of answers, it is the refinement of questions. And for the first time in decades, cosmology does not know what it will find next.